So, in the last class, we were talking about the practical issue of how these S parameters are measured, and the basic idea is simple. We have some sort of cable connecting the measurement equipment, which is basically some box, right, and so basically an impedance measurement unit, and what it does is in terms of the reflection coefficient gamma, all right. And the transmission line, I mean, in our idealized analysis, we have basically assumed that our transmission line is it's got some characteristic impedance Z naught and some delay Td, and as we were discussing yesterday, while in principle Z naught and Td can be determined accurately, in practice, as users keep changing cables and whatnot, and therefore all that we can say is that we have an unknown reciprocal 2-port, and therefore there are, if you think of it, impedance or scattering matrix, you basically there are three unknowns, namely Z11, Z12, Z21 and Z22, and Z21 is known to be the same as Z12. So, the three unknowns that need to be determined, and obviously you cannot determine these three unknowns without three equations. So, the idea is before you put the Z dot, right, you put a short circuit, you have an open circuit, and you have 50 ohms, which is a standard, right. And which do you think, this 50 ohms better be very accurate, because remember that we are measuring reflection coefficient which is dimensionless, and our final impedance of Z dot has got dimensions of ohms. So, somewhere along the line they must come in a quantity with dimensions of ohms. If that is messed up, then all your measurements will be off by whatever factor that that Z naught is imprecise by. Does it make sense, right? So, if you thought it is 50 ohms, but then like you do your homeworks, you basically cut corners, and then the 50 ohms is 54 ohms, right? Then all the measurements that you make will be off by 4 by 50, right? Simply a scaling error, right? Because Z naught will appear somewhere in all those calculations. Okay, and so therefore, and this notion of open and short also needs to be when you say a short, the short basically means that the electric field at that point is actually 0, right? And open basically means the magnetic field at that, you just can't take two wires like this which are played open like this and say it's an open circuit, right? For example, so let's say I claim this is a short circuit. I have two wires which are spaced 2 inches apart, and then I connect these two and claim this is a short circuit. Can somebody comment on whether this is really a short circuit or not? Yes, Devrin? Yeah, okay. Yeah, so basically, right, as you can see, if you go and connect this to a transmission line, well, you have a loop here, and any loop has got inductance, which is equivalent to saying that as frequency keeps increasing, what you thought, it's definitely a short circuit for DC, but as the frequency keeps increasing, it is no longer a short circuit, right? So a short circuit is simply not arbitrarily taking 2 points and connecting them with a wire. It has to be engineered properly so that it is truly a short circuit, and there is obviously some art to it. It is not straightforward, right? And likewise with an open circuit, and likewise with the 50 ohms, right? This 50 ohms at least must be 50 ohms across your frequency range of interest, right? So this box that you buy after paying a lot of money basically will be designed, and so will these are what are called impedance standards. Right. So these will be very carefully machined, and the material will be chosen so that over the ambient temperature range, the 50 ohms remains the 50 ohms. The open circuit and the short circuit remain opens and shorts over the frequency range of interest. As you know, it is impossible to make an open circuit or a short circuit be open or short for an arbitrarily wide range of frequencies, right? So when you buy a box like this, you will also get a jewel case where you put these where it also comes with these impedance standards, and before you make a Z-dot measurement, you will first. So this impedance measurement box basically, as we discussed yesterday, has got some way of separating the forward going wave from the backward going wave, and is able to therefore measure a reflection coefficient as a function of frequency, right? And let's say you want to measure the impedance over a range of frequencies, which is what you typically want to do, right? Then you must measure the reflection coefficient over a range of frequencies, correct? And what do you think you will have to what do you think is there inside that box? What all do you think you would need inside that box to be able to make measurements over a range of frequencies? Pardon? I cannot hear you. What is the frequency tuner? Yeah, you basically need a sinusoidal signal source, whose frequency can be varied from over the range in which you are interested in making the measurement, right? And so you have inside a variable frequency sine wave source, right? And and once you are able to separate out the forward and the backward wave, you can measure the phase of each of these relative to a standard. For example, remember that gamma is a complex quantity, so it's got both magnitude and phase. So you want to be able to measure the phase of the reflected wave in relation to the phase of the incident wave. So it's not merely enough to measure the power of the reflected wave, you also need to measure its phase, right? And so there is some sophisticated electronics inside which enables you to do this accurately, right? And and all this stuff comes packaged with Windows operating system and what do you call nice GUI, so that you can press button and then it does all the stuff that's needed for you. So it will sweep so the measurement process is as follows. You turn on the box and then you wait for the operating system to boot up, and after you are done, then you connect the short circuit standard there across the cable, right? The cable is there because this is a big box, this size, and then your impedance is some tiny thing somewhere there, right? So you connect the cable to that between the box and the device under test. But before you do that, you must connect it to the short, and then you press some button, and then the box will basically sweep frequency over the range of interest and measure the reflection coefficient as a function of frequency, right. That is let us call that gamma A. So, measured gamma with z dot equal to 0. Okay. Then you press another button, you remove the shot, and then you have the measured, and redo the whole thing with z dot equal to infinity. Gamma C is basically the measured gamma with z dot equals 50 ohms, and then gamma X, which is measured gamma with the actual z dot. Okay. And as we discussed yesterday, the aim of these three experiments is to basically obtain Z11, Z12 and Z22 as functions of frequency, right. Once you obtain these are the functions of frequency, well, it's pretty much straightforward, algebra to go and find what the true reflection coefficient would be, provided this 2-port wasn't there, all right. And that's basically basically what is done in right. So, this is this instrument is what is called a 1-port vector network analyzer. Are often abbreviated as VNA, all right. And a VNA is basically what do you call just like how if you want to have an electronics lab, you must have a multimeter and an oscilloscope, right. If you want to do RF and microwave work, you always want to have a VNA is basically as ubiquitous and necessary as a multimeter is or an oscilloscope is for low frequency work at microwave frequencies, at RF and microwave frequencies. And as we discussed yesterday, the notion of what constitutes RF and what constitutes microwave is a function of this quantity omega times Td, right. And omega, as you know, is 2 pi f, and Td is nothing but, well, the distance, let us call it the length of the line divided by the velocity of light, right. And C by f is nothing but, C by f is lambda, right. So, basically this L by lambda is what constitutes, there is nothing which is absolutely high frequency or nothing which is absolutely low frequency, correct. Everything depends on the ratio of distance to wavelength, right. So, for example, if you are working on a single chip, right, where let us say your chip dimensions are half a millimeter by half a millimeter, okay, and you are working at 3 gigahertz. Can you comment on whether the circuit is can be treated as lumped or or can be treated, for instance, let us say I have a line which is 20 microns long on a silicon substrate, right, okay. And the frequency of operation, the maximum frequency of operation is 3 gigahertz. Can we comment on whether this constitutes, do we need to use distributed circuit theory, or we are good enough working with lumped circuits? You have a piece of wire, how would you represent it, what would you do? Yes, Ajay Kumar Reddy, what do you think? What is the wavelength? Again, you guys got to get used to the notion that speed of light is 3 into 10 power 8 meters per second only in free space, right. On silicon, it will be a factor of, the dielectric constant of silicon dioxide is roughly about 4, right? So it's basically a factor of 2 smaller. So a good number to remember is that on silicon, the speed of light, I mean, again, this 3 into 10 power 8 meters per second, right, is a number that only makes sense when, you know, you're dealing with, right, the sun is, so many billion miles away from the earth, okay, and then 3 into 10 power 8 meters per second, you know, makes sense. You can calculate that sunlight takes 8 minutes to come from, you know, the sun to earth, right. On an IC, you're not dealing with seconds, you're not dealing with minutes, you're not dealing with seconds, you're dealing with microns and picoseconds. So it's always much easier to express the speed of light in microns per picosecond. So 150 microns per picosecond is the speed of light on silicon. In free space, it is 300 microns per picosecond, right? If you have a millimeter on silicon, it's about 6 picoseconds, right? 6 to 7 picoseconds. Anyway, so 20 microns is how many picoseconds? How long will light take to traverse 20 microns? Yes, Karthi, what do you think? Okay, right, something like less than a tenth of, about a tenth of a picosecond, right? So, and how does it, how does that a tenth of a picosecond correspond? How does it compare with the frequency of operation? Let's assume we are working at 3 gigahertz. Right? What is the period corresponding to 3 gigahertz? It's 330 odd picoseconds, right? So basically, the sine wave basically, if this is 330 picoseconds, right? And this is a tenth of a less than a tenth of a picosecond, right? So this j omega TD therefore is so small that for all practical purposes, you can treat a 20 micron wire, right? If you're working at 3 gigahertz, you can treat it as a lumped element. And what kind of lumped element will that be? Okay, resistor is true at DC. If you go slightly at higher frequencies, what all do you need to do? So basically, you basically treat it as you can treat it as perhaps an LC network. Many times the L will be so small that L can also be neglected, right? Depending on the rest of the circuit in which this lumped piece of element of metal is embedded, right? Most often times in IC work, for example, if you're working at the low gigahertz range, you will be, your layout extraction tools are quite happy modeling a wire as a combination of resistance and capacitance, right? If you have a very long wire, you break it up into small wires and then, all right. So on an IC, for example, for that matter, for example, therefore, the absolute frequency 3 gigahertz is of no fundamental consequence, right? It's as easy or as difficult as assembling things on a breadboard, right, at a much lower frequency, because on a breadboard all physical distances are larger or smaller, are much larger, and therefore what constitutes a high frequency on a breadboard is in absolute numbers much lower than what constitutes high frequency on an IC chip, right? And those of you who've taken a power systems course, right, what is the frequency of operation? What is the frequency of operation? It's 50 hertz, right? But now you have a transmission line running from, from Timbuktu to Tamil Nadu, right? So basically, these lines are so long, right, that there again, even though the frequency is 50 hertz, and you might think, what is 50 hertz? 50 hertz is DC, right? Okay. But the point is not whether 50 hertz is large or small, right? It is all to do with the physical distance over which you're working in relation to the wavelength of operation, right? So, 10,000 miles of transmission line working at 50 hertz, right? Distributed effects become, just as important and, crucial as, working at 3 gigahertz on, at say 3 gigahertz on a benchtop table, right? Whereas the same 3 gigahertz counts like, you know, I mean, you don't have to worry about distributed effects if you're working with 3 gigahertz on a chip. Does it make sense? All right. So, so this is an example, as I was mentioning. This is an example of what is called a one-port vector network analyzer. Let's kind of the one port, that makes sense simply because you're only measuring you know, the impedance of a one port network, and of course it measures, it analyzes a network. So it's a network analyzer. Why is it called why do you think it's called a vector network analyzer? And if it is not vector, what would it be? If something is not a vector, what is it? Okay, well, so there must have been something called a scalar network analyzer before the vector network analyzer, right? So why do you think you have a vector network analyzer? So basically, it's called a vector network analyzer because it measures both the magnitude and phase of the reflection coefficient. So you know, it has only become possible to do this over the last maybe 30-40 years or so. I mean, or 50 years, right? Before that, they used to have what were called scalar network analyzers, which only measured the magnitude, and then you know you had to basically you know, do something a lot more I mean, involved to be able to infer the phase, you know, making additional measurements and so on. Because earlier you would only be able to measure power, right? You not, now you have sophisticated electronics which basically is also able to measure the phase in addition to the magnitude, and so this is why these are called a one port. Why is this? These are called vector network analyzers. The next thing is, oh well, you know,